All right, let me see. Well, we're going to wait just a few minutes as folks start to come on in, but we are glad to see you and glad that you're here joining us for our talk today. As you come on in, I'll do a couple of announcements. You so first off, if you were here with us last month, you probably remember we did have like a Zoom bombing, and so we're a little bit stricter now on like who can unmute, and there's a few so you may notice a few more restrictions on what you can do in this Zoom room. So thank you for working with us or being patient with us on that, making sure we keep this to be a friendly and professional space. Related to that, I guess, we have been trying to keep the lid on spam, but there's been a little bit uptick in spam on meetup.com, and we've been deleting and reporting that content. But certainly, please use your judgment about things that look to be scammy. Almost certainly are. We're working to keep those deleted and whatnot, but please do be aware of that. And you also can report any content that looks to be spam or scams there. So that's a little bit of some logistical type things. I think that most of you all found us via Meetup, and like that's how you know who we are and whatnot. But I will drop that link here for you all just so that you can see that and where you can find out about us. We do use the R Consortium's community code of conduct, and I'll drop that here as well. So much as if we were in person with each other here in this space, we want to this is a space that is a friendly and professional space, and Andrew and I are the moderators, and so we're really glad you're here, and we want to keep this to be a space that is where we can learn and have a good experience for folks who are here. We are taking the month of December off, so we do not have a meeting happening in December. And then we, in January, are going to have our community lightning talks. So this is something we've done for a number of years, having that January meeting be a lightning talk meeting. So I'm going to drop that link here so that you can see and join and sign up to join, but also maybe that you could consider giving a talk. So the idea of these lightning talks here is that they're like 5 to 7 minutes total. Like this can be a great opportunity if you have not given a lot of talks before to try out giving a talk on the topic. It will just have them kind of like rapid fire discussion, bam, bam, bam. So there's a link in there, but I'll directly send you the link here that you could consider submitting submitting a talk here. So we um the meeting will be like this one, online, open to everyone. I think we are gonna see who signs up, and if we end up with a lot of people who sign up, we probably are gonna give preference to people who are local Salt Lake City or Utah area people. Just so you're aware of that as you decide to submit. I think that is all the announcements. Is that right? I think that is right. That's what we've got for announcements here. So I am quite excited about today's session that we have. I'm really glad that you all are here and that we get to share this together, because I'm really interested in like learning about applications about how people use R, and this one looks really, I'm very happy for us to get to learn this. So I'm going to introduce Brennan. Brennan, thank you so much for coming here and preparing this
Sure.
talk. Brennan is a professor of stats up at Utah State University. Brennan, you work on your research focuses on applied environmental statistics, and you study snow. You study snow, which we don't have much of yet, but like can have such impact here. And so we are really glad. Thank you so much for preparing this talk, for being willing to come and share this with us. We're really excited to learn more about how you use R in this particular application to do the things that you study.
Yeah, thanks, Julia, for that introduction. pull up some slides here.
While you do that, I'll just tell folks if you have questions while we're going along, you can type them in the chat. I will keep an eye on. There is that like Q&A section. If you type something in there, I'll see that as well. So if you as a listener have some question as we're getting going, you can type it, you can put it in the QA. You also can do the raise hand thing, and then we as the moderators can unmute you, and we will have some time for questions at the end, we think. So awesome, Brennan. Thank you so much.
Yeah, and I won't be looking at the chat while I'm going, but I will make sure that there's 10 to 15 minutes here at the end that we can discuss. And so uh, my talk is about how I'm using R as the great orchestrator on this problem of understanding the evolving threat of snow loads. And when I say snow loads, I'll show a picture, but we're talking about the weight that snow induces on structures, typically on the roof, and that can lead to collapse. And so, just a little bit of background: I'm part of a some task force that I don't know if my mouse can be seen, but this ASCE 7. This is a document, and I'll show a picture of the book. This is what the US uses to define minimum design standards for buildings and other structures. And so I am the lead author. In fact, I saw Jaden Wagstaff on the call. He was the brains behind the ground snow loads, from which we then infer roof snow loads for ASCE 722, and currently the co-lead of the Snow and Ice Task Force, where we're trying to think about how design standards should change with a changing climate. So for the first time, the U.S. minimum design standards are thinking about climate change as being part of the standard, and I'm developing that in a well, in real time. And this talk is part of what we're proposing in real time, and seeing if we can get accepted into the standard. And so lots of names, and not every name's here. I just mentioned Jaden Wagstaff as one who has helped years ago. These are the names of the people working on the ongoing project with NOAA, looking at this climate change, and just mentioning that some of these slides come from them, and I don't remember who comes from what. So we just got all the names listed here, and another group of people that from which slides come from. And I think the most important thing to emphasize for this group is in the same way that R can be used to pull in different softwares and packages to do one thing uniquely well. These kind of problems require engineers and policy specialists and climate scientists all coming together to solve that problem. And I think that the role of the statistician, the same way that the role that R plays, is being the orchestrator, being able to talk to each of these groups to do something that no one group, and especially the statistician, could do on their own. And so I went to the USAR conference in Durham this last year, this last summer, so summer of 2025. And Simon gave a talk, and he called R a data analytic language. And that like really caught my interest. And then he called R the orchestrator. And that's where the title of my talk came. And so here's a an orchestrator, someone bringing people together. And it really spoke to me about R's ability to bring not just different packages in R, but different languages together in this really, really interactive way. And so I love this John Chambers quote, going back to the S days, when he talked about this desire to have a framework where someone starts in an interactive environment, and then as their needs evolve, they slide into programming. When 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 A, you get better at understanding the system, and B, when you start to better understand the problem. And so this idea of R as being this thing that brings all these instruments together really resonates with me. It resonates with me as an applied researcher, that I'm not spending a lot of time making instruments, but I do spend a lot of time thinking about how these instruments can play in ways that no one's ever played them before, play together in ways that no one's ever played them together, the same way that leading an orchestra might look like. And so just at the highest level, what we're trying to do is we're trying to design structures that are cost effective yet safe enough to withstand environmental hazards. So I'm looking at snow, but there are research teams looking at extreme wind and flood and tsunamis, tornadoes, ice, and how ice accretes on like electrical wires and can bring down substations. And so engineers are trying to find this balance. We need things to be safe, and we need them to be really safe, not just kind of safe. No one wants their home to have, for example, a 25% chance of failure in a 50-year period. We need those to be less than 1%. But at the same time, we have to make these structures cost effective. Um, we can't make everything a bomb shelter or a mission critical military installation. And so ASCE 7 is a book made by the American Society of Civil Engineers. It's a consensus document, so it's all volunteers like myself, and they are writing proposals for what should be the minimum design standards. So anyone can do more. This is supposed to be the lowest that people can go if they adopt it. And that is meant to target a certain probability of failure, which we'll talk about in a little bit. But one of the cool things about applied research and R helping me do this is trying to navigate uh, science, computation, and policy. So we have to do something that's computationally feasible and that people will believe. So if the model's too fancy, then you have these issues with policy that people won't accept it. And if you use a fancy model, you have to be willing to explain it to people who have, no background in statistics. And so what I'm going to do now is just show you a list of packages and it's meant to be overwhelming. And the point is that we have this process. It's on the right hand side here where we're starting with raw measurements of snow and we're getting down to this continuous database of minimum design standards. If I'm in Logan, Utah, which is where I'm located, how much snow does my roof need to hold to control the probability of failure to be 0.13% in a 50-year period? And so we're going through this process of inferring weight of snow when we only have its depth and doing an extreme value estimation on annual maximums. And each one of these packages plays different pieces in this symphony of trying to go from raw snow measurements to that final data set. Adele Cutler was a faculty at Utah State. She wrote the Fortran code of Leo Bryman's original random forest. It's, I mean, since been adapted multiple times. And she told me, I don't know if she came up with it, but I can't find an attribution otherwise. By the time you finish, you're ready to begin. And so definitely as I present on this applied research and I look back, it's like, man, I'd love to do it again, knowing what I know now. But the key advantage that R provided was we didn't know what we were doing. We didn't know how to navigate through this workflow. And R always provided the thing we needed when we needed it. Uh, um, Either through a package or through the ability for us to develop our own package, which we did on a couple of occasions. Remap being one of those packages that Jaden Wagstaff, who's on the call, developed and is available on CRAN. And so that's kind of the beginning with the end in mind. So let's go back to the start. What are we trying to do? Well, we don't want buildings to fail when snow accumulates on them. And so what we do is we play this game with two random variables. One is the resistance of a structure, and that is how strong the structure is to resist a load. And load is a random variable, and loads can be things like winds, tsunamis, these types of things. We're looking at snow. So snow, extreme snow follows a probability distribution. It's really a compilation of multiple random variables as we think about how snow is retained on a roof given its geometry. But at its simplest level, snow is a probability distribution. We don't know how much snow we're going to get next year, but we have some expectations about what the pattern might look like year to year. We then have resistance, and we want resistance, black, to be bigger than load. And so we want the intersection, the possibility of a load exceeding a resistance to be really, really small. And how small is ridiculously small? So small that you kind of have to sell your soul as a statistician to be in this space because you're doing some incredible extrapolation, which we handle with robust statistics, smoothing methods, and now looking at Bayesians with strong priors. But I'm going to focus on this risk category 2. So if you're in a home or an apartment complex, you're likely considered a risk category 2 structure. And so this beta equals 3 is just a z-score of 3 on a normal distribution. And what we're saying is that we want the probability of failure in a 50-year service life. Many buildings last longer, but that's kind of the calibration window to be 0.13%. So a 0.13% chance of failure in a 50-year period. If you annualize that probability of failure, it's like a probability of failure once every 35,000 years, which again is crazy until we think about the sheer number of structures that we make, which are not independent, but communities might be considered independent, that we have 10,000. Let's suppose we have 10,000 independent, statistically, from a climate perspective, communities across the United States. We're really saying that we don't want to see a failure in any one of those communities more than every 2 or 3 years. So all of a sudden, this ridiculously low probability of failure from an individual structure is a moderately low probability of failure when you think about the building stock of the United States and making sure that we're not having homes collapse all the time, even if it's not that many relative to the building stock. So we have a load curve, a resistance curve, we have a target probability of failure, and this whole thing is really just how do we do Monte Carlo simulations to calibrate what the resistance of the structure needs to be in order to target these different probabilities of failure. And so it comes down to in snow that we have three different maximum generating processes in snow that we have to think about. And that, so the one is red. This would be like the mountains of Utah. We get snow for months. It starts in November. We keep accumulating until March or April, and and we get a curve that looks like red. The upper tail has been tamed by the fact that we're summing individual storms. It's not the central limit theorem, but it's a similar effect. Uh, Blue is in the middle. The other contrast are places like Baltimore, Denver, where they can get several feet of snow in a single storm, and that tends to be the maximum generating process. So the largest snowstorms in a place like Baltimore or Washington, D.C., are generated by one or two storms in a short duration, 1 or 2 weeks, that just have an incredible amount of precipitation. And the key is that the tail behavior of a mountainous snow accumulation versus a Washington, D.C. snow accumulation are different. And so past engineering paradigm would say, we're just going to take the 50-year mean recurrence interval, so the 98th percentile on any one of these curves, and we'll multiply it by a fairly large number, 1.6, to bridge the gap between a observed load and this probability of failure. Well, what we're trying to do now is simulate from the tails of these distributions to calibrate what we call reliability targeted loads, where the load we prescribe targets the probability of failure, which is an interaction between a load and a resistance, rather than just thinking about only the snow in isolation, which we call a uniform hazard. This is there's a lot of engineering terms in here. The key point here is I need to use R to do Monte Carlo simulation on different kinds of snow, annual maximum snow curves to figure out what the middle of my black curve should be. That's what I'm trying to do. And so you've already seen this workflow, but we have to start with actual measurements of snow. Sometimes we have to estimate the load. We then do an annual maximum process. We do this by water year. So we're collecting the annual maximum snow weights in each year. We fit probability distributions to that process, and then we simulate from these probability distributions to get reliability targeted loads. Then we have to map them using information about the surrounding climate in order to fill in the gaps where we don't have measurements. And so back in 2020, we did this with these stations. Blue dots are our best stations. Orange are stations that we tolerated with smaller sample sizes in places where we didn't have blue dots. And the purple dots are places that don't get snow, but we kind of needed them as almost like a zero padding so that we understood how we're transitioning from no snow regimes to places where snow actually does matter and affect design. And so one of the first things we had to do, and you'll now notice that on some of these slides in the bottom right corner, I'm naming our packages that we used. We very well could have used Ranger here at the time. This was 2020. It got published in 2022, but it was 2020. We were familiar with the random forest package. And so one of the issues that we had is that all of the ways that people were converting snow depth to snow weight, there was only two kinds of mentality. So one was only looking at airports in the United States. And that kind of is like this purple curve right here. And the other curves were only looking at mountainous snow that accumulates for 5 months. And we needed a way to kind of learn whether a place had mountainous type snow or airport type snow for places in between, like you know, I'm trying to even think like Park City. How close is Park City proper to being mountainous ski snow versus more like Salt Lake snow? We know it's more than Salt Lake, but it might be somewhere in between. And so we used random forests to, and you can see the orange curve is trying to learn the depth to load relationship as a function of the surrounding climate and proximity to coast. And in Salt Lake, it did a fairly good job of basically capturing these mountainous curves and airport curves. But we felt like it gave us a mechanism to do things in between those kind of regimes. And so then once we had snow weight either directly measured or estimated. And excuse, I should have taken this off. This slide was originally given to people that didn't understand statistics, but we're taking the annual maximum, we're fitting a probability distribution to it, and we use the generalized extreme value distribution. Again, pointing out the EVD package, could also use the EXT Reams package to fit these snow loads. And this was an innovation that was brought to the problem before everyone would just use log normal. They assumed every annual maximum snow process was a log normal distribution. And what we found is that the mountains are a GEV distribution or the inverse Weibull, which is GEV with a negative shape. And other places had really heavy tails, which is a GEV with a positive shape. And this curve is meant to illustrate that. I think the key point for this group is that R had a lot of packages that helped us get started with this distribution fitting process. We had multiple options. We were able to interact with these options. We settled on EVD, but we could have used a laundry list of other packages. And so once we have these distribution fits, we're then thinking about, well, how would we simulate from them and what would reliability targeted loads look like? This slide's more for the engineer, but it's emphasizing that we're not really interested in what's happening with typical snow. We're interested in an extrapolation of the pattern in which we receive snow and how that helps us affect this really, really small target probability of failure. And so communities like Minneapolis that typically get a lot more snow than Baltimore end up having the same design standard because we're not interested in what's happening typically. We're interested in what might happen in a super extreme year. And Baltimore is one of those places where it's warm enough that they don't always get snow, but it's also a place that gets lots of water in the wintertime. And so, in the right combination of conditions, where we take that 33 degrees Fahrenheit, we take it down to 30, all of a sudden you can get tremendous accumulations of snow versus Minneapolis, which is always going to get snow, but gets also substantially less water in the wintertime. And so this map shows the shape of the probability distribution across the United States. It uses the EVD package, MGCV, generalized additive models with splines on the sphere, paired with a package called Remap that's also on CRAN that let us fit local models, models within polygons, in this case ecoregions, and stitch them together so that we got these smooth, continuous measurements across these subdomains. And so purple means the snow probability tail is heavy, and orange means that it's light. And so northern and mountainous locations have light tails, mid-latitude locations have purple tails. And so what we then have to do is we need to simulate snow load, snow retention on a roof, resistance, and put all these things together and to get this target probability of failure. Those distributions are not tractable. There's not a mathematical way to calculate the distribution of the difference because we're using distributions from different families. And so what we do is we create a tiny little shack. It's got a 30-foot span, a 30-foot width. We design it with a steel beam that weighs, that has it's a dead weight or self weight of 15 pounds per square foot. We run through all the engineering calcs, and we're doing this all in R using what's called a limit state. And so engineers will combine different loads. Each of these letters represents a different random variable that we're simulating from. And so we use statistical theory to cut down on the number of simulations that we need, but then we use RCPP to do these simulations. And one of the reasons we moved to RCPP is, and it's evolved over time, is that we could just do the simulations faster in RCPP than we could even using a vectorized implementation in R. And the key point for this audience is that we started, all of the ideas were developed using vectorization in R. We then hit a ceiling on, we need this to run a lot faster. We need to be able to parallelize it. And RCPP provided this really natural on-ramp to do all of those things. We didn't have to switch systems. We just simply had to extend our process, add one more instrument to our, the orchestra that we were building in real time. And it felt fairly seamless in a package development environment. And so we get these simulations, we get reliability targeted loads across the country. We then developed our own package to do this stitching. So MGCV fits generalized additive models with splines on the sphere. And so within each one of these colored regions, we're using a generalized additive model to estimate the snow loads on a continuous grid. And then we developed our own package to stitch all of those submodels together so that an engineer would never see a snow load jump when they moved across some boundary that they didn't know about. We needed, from a policy perspective, the the estimates in this geodatabase to smoothly transition. And Remap was our solution to that, where we did weighted averages, not based on distance from centroid, but from distance to boundary, because some of these boundaries are very, they're weird, and the centroid is not always a good, it's not a good reflection of the distance between these different ecological regimes that we're looking at, mountains versus valleys, deserts versus maritime, things like that. And so now what you get is there's a website called ASCE7 Hazard Tool. If you want, you can type in your home address and you can click that you want to know what's going on with snow. In this case, you can click on some of the other hazards. You view results, and that is depending on what state you're in. Not all states adopt the federal standards, would be how people are designing your house, although more likely commercial buildings. Most of these standards are used for commercial buildings. And so that was a like 5 years of work in like 15 minutes. Um, and what I wanted to then talk about is, and I think this goes to this, how R let us continue to adapt, is we did this thing 5 years ago where we're just thinking about historical snow, coming up with a geodatabase. We then got asked, well, what are we going to do in a future climate? How will all those estimates that we made 5 years ago hold as as the climate changes? And and so we then have to learn on the fly, and there's a lot of words on this. And the point of this slide isn't to go through all the words. The point is that we had to learn, my research team, an entire vocabulary of climate science on the fly, and then figure out, okay, with all of this vocabulary and all these new data sets, how are we going to determine how snow will change in a changing climate? Spoiler alert, in most places it will be less of a threat, but not necessarily everywhere. And I'll show the map at the end. And so now we have to weave into this and I've listed SF and Terra down here. So we're thinking about these the spatial data as can be looked at in the SF package. So in situ measurements for like point valued stations, SF was the framework by which we handled that. Now we have to think about these gridded climate models where we're thinking about a mesh of climate projections going down out to the end of the century. And for that, we're now looking at raster data, and the Terra package was what we needed to move to. That was the new instrument that we needed to think about these variable infiltration capacity models um, from the that were run on the coupled model intercomparison project. Sometimes you've heard of CMIP or RCP. Oop, going all over the place. These are different emission scenarios and they're different climate projections. And we were able to look at all of those using the Terra package in R. And so we don't know exactly what we're doing. We know we have generalized extreme value distributions of extreme snow. So we started with just thinking, let's leave the shape parameter constant because it's too hard to, we don't have enough data to fit it reliably in a future projection. But what if we allow the location and the scale of the generalized extreme value distribution to vary in a climate? And let's just let it vary linearly. And for that, we were able to use the IS, I don't know if it's the ISMEV package, ISMEV, I just spell it out, that let us fit non-stationary extreme value parameter estimates. One of the great things about R was that there was some very specific things we wanted to do that this package wasn't letting us do. But because the package was open source, we were able to take that source code and adapt it to do the thing that we wanted to do, which proved to be just purely experimental. We weren't going to take that adapted code in production, but it just highlights the the thing that I appreciate about R most, which is its ability to interact, to test, and to have that just be very native and natural, and going from not really being programmers and more data explorers to programmers without really realizing that we were doing it. It became a soft introduction. And so we just decided we're going to look at, there's all these different model runs. So we're running on the same emission scenarios. Different teams use different physics in their meshes. They initialize these models with different parameters. So let's just let them all vote. So it's kind of like the electoral college for climate models. We're just going to see if the trend in these coefficients is positive or negative, and if it's statistically significant or not. And if it's statistically significant and positive, we'll let them vote one. If it's negative, we'll let them vote -1. And so we're looking for a consensus in the direction in which these parameters might be changing over time under the assumption that they're linear. And so green means that more models said that the parameter was going to get bigger, in this case, only looking at the historical period, so 1950 to 2020. Red means that even in the historical period, we're anticipating that the snow was declining. And so when we look at just the history, it's kind of a mixed bag, mostly light colors. When we move to a moderate admission scenario, we see that the coastal mountains of the West start to have a consensus in that snow will be reduced. And by the time we get to RCP 8.5, almost all of the country, except for this weird pocket in the upper north Midwest, are seeing substantial declines in snow over time, which is not, the pink is not unexpected. The fact that this upper Midwest is not as pink was kind of the surprise for us. So looking at the scale of the distribution, it's the same story, that more emissions, less smaller scale or less variability in this GEV. But then we ran into another ceiling, which is, well, but snow's not really changing linearly. That some of the climate science we're looking at suggests that there are some areas that might see an increase in snow with small increases in temperature and then a decrease. So the initial increase is due to the fact that the atmosphere can now hold more snow, but that once the temperature increases enough, then our snow season shortens and we lose the gain in snow that comes from holding more water in the atmosphere. And so we now need to think about non-stationarity in these parameters uh, as nonlinear functions of time. So now generalizing to just be some function of time rather than a linear function. And so just as a quick side story, I'm getting asked to like do this just this last summer, and I have like weeks to come up with a solution. And so I'm not in a position to develop something from the ground up. So looking at the literature, having conversations with large language models, and learning about this EVGAM package. And again, one of these opportunities in R to find the instrument that you need when you need it to help you finish the song or the analysis that you're trying to write. And so EVGAM was designed to run generalized additive models on extreme value distributions. It's almost like I prayed it into existence, like this divine gift that had come down. And so we were able to then think about all of these things now as generalized additive models with the same penalties that MGCV gives you for preferring simple GAMs unless otherwise needed. So a lot of the times the effects still look linear, but occasionally, like it does in Duluth, Minnesota, the location parameter sees that increase in the short term followed by a decrease in the long term. This gap in the middle is just meant to emphasize that what we were trying to do with the future climate is run a reliability analysis on two 50-year periods. One was 2020 to 1970, because 2020 is when we ended our previous study. And then the next period is 2030 to 2080, because no one will use any of these climate change factors we come up with till 2030 at the earliest, just the way that the bureaucratic process goes with updating design standards. So we put the gap in to say we're going to do two reliability analyses, one in the past, one in the future, and we're going to look at the difference, the relative difference in the reliability targeted loads we would have obtained to come up with what we call the climate change factor, which is how would we need to adjust our snow loads in a future climate? And EVGAM let us think about non-stationarity in a nonlinear way, which is exactly what we needed for this project, but didn't have the time to develop ourselves. And so we then go back to RCPP to now do the simulation of the Monte Carlo simulation in a non-stationary setting. And so we're no longer just simulating 50-year loads, which we can use some math to simulate 50-year loads in a stationary setting. We're now simulating evolving distributions. So the distribution is changing each year, and we're simulating one value per year from a different distribution and using the standard library in CPP to take the maximum from each 50-year period to develop a non-stationary aware distribution of loads and resistance over the service life. And so in some places, so now we have a simulated distribution for the past and a simulated distribution for the future. We can then calculate the reliability targeted load from the future divided by the past to get this climate change factor. And so I don't want to, for the sake of time, go into all the climate assumptions. We had to make a lot of assumptions about what's moving in the changing climate and what isn't. And that's a conversation for another day because we're talking about R. The conversation that I do want to have is that we had to do this process on these maps. There were 62 of them, 31 for a moderate emission scenario and 31 for a high emission scenario. And the process was very computationally intensive. It took about 5 or 6 days to run on my desktop. We didn't have a supercomputer. We weren't set up to run on a supercomputer because we didn't know what we were getting into at the time. And so this is where the future package saved my life. Well, Tara saved me. Tara does really fast computations on rasters, which we appreciated. But we now needed to do it 62 times. And so this is an embarrassingly parallel problem. Each of the maps we can look at completely independent of the others. We just have to do them. And so what Future allowed us to do was parallelize across the maps really simply. So not having any experience with parallelization in Future and not wanting to parallelize on the individual map level, being able to then literally commandeer some desktops, again, because we needed to do it quickly and we didn't have supercomputer access because we didn't know that's what we needed, to let the Future package naturally let us parallelize this across 3 different machines and get it done in about 2 weeks and right in time for us to um, uh, turn in the results. So what we did is we took all these 62 models and we started looking at statistical summaries of the change factors across those 62 models. And so what we settled on was across the 62 models, the 75th percentile. Purple is where the climate change factor was be above 1. that we would recommend that snow loads need to go up. Anything that's gray or orange would be places where we'd recommend that the snow be the same or go down. The engineering community decided that they don't want to ever reduce loads due to climate projections. They only want to allow increases if there's evidence. And so we ended up with this map. So all these R packages came down to this map, which says if you're an engineer and you live in this region that's inside of the contours, you need to slightly adjust your snow loads up to account for the change in climate by the end of the century. And so some of the things that we learned about this um, from like a science standpoint was this idea that snow is mostly going down, which we expected, except for the upper Midwest. There's some literature that suggests that the way that the continent's warming, that portion of the continent is kind of spared from some of the other drastic increases that we see in temperature. Um, we proved that we could, not just in R, but generally do this in a fully simulation-based approach. The kind of state of the art of engineering is to not do it so explicitly with simulation like we did with these Monte Carlo simulations and everything. And it seems like the future is going to require us to think in these gridded terms. So instead of just thinking about weather stations populated across the country, we need to think about um, uh, these climate products that think about uh, climate statistics on a continuous grid. And so now to bring this back to R, some of the reflections. Here's a um, someone leading an orchestra. Um, the key to success for us was the ability to interactively explore. We did not know what we needed to do, so we needed to mess around to find out what we needed to do. Once we figured that out, it was convenient to stay in the same software paradigm to create something for production rather than having to transfer to something else. And so when we pushed R to its limit, we were able to use C++ to take us the rest of the way, which allowed us to blur this line between data exploration and package development. I can't tell you when I was developing and when I was producing. Maybe my students can. Eventually, once we got a solution, they'd go make a package and write their thesis or dissertation about that package. One thing that I haven't really mentioned is the role of large language models. One thing, I'm still trying to learn how to use them myself, but one thing that was really impressive to me was asking a large language model to give me the inverse normal function, which is not a closed form solution in C++, and it was perfect on the first try, and it took like 5 seconds. And but one of the things that I want to emphasize is that like that can only help us do things we've already done. So we need a community that's pushing the envelope. And so anytime I had a success asking for R code, I know that that was a product of a community that had developed creative solutions that that large language model could train on. And and so I'm grateful for that community, and I hope we don't lose it as people defer to large language models more and more for some aspects of code development. And so I want to end with a thank you for the instrument makers of the R community that let us put together this song, that let us create the first ever climate change aware standards for snow load design in the United States. Um, I'm happy to take questions. I will mention I only referenced literature that wasn't an R package. All of the R packages I named, I didn't have citations. I didn't think anyone would actually read them, but if you type in the names, they're all CRAN packages, so you should be able to find that information based on the package names. So thank you, and I'm happy to take questions. Um, and I guess I'll stop sharing at this point.
Awesome. Thank you, Brennan. That's super interesting to hear about that massive project and everything that went into it and how the approach that you took. We got a couple of questions from folks that are here. The first one was about your use of RCPP. So you said, if I remember right, if I'm rephrasing this correctly, like you use that in the simulation, like for the
Yeah,
simulations that you did. And when you were had you used a lower level language before? You came up through like you are a statistician by
yeah,
training.
yeah,
Like did you use it? How hard did you find it to get going to integrate
yeah.
it into R? And then this person specifically was asking about parallelization, like how like if you like like
Yes.
on like working course. What was your experience like when you picked up using our CPP?
Yeah, so I had to, as a math major back in the 2010s, take it. It was still C++ plus plus as the intro language. So I'd had
Mm,
experience. They hadn't moved to Python yet.
yeah, yeah.
That being said, our CPP is it's kind of like Spanglish in that it's not C++, plus plus, but it's not R. It's somewhere in between. So it's kind of its own entity. And so picking that up with all the great documentation that Dirk, I don't know how to say his last name, Edebichel, how do you know how to say it?
Edelbutel, I think. Edelbutel.
Edelbutel?
I think is
Okay.
how you say his last name. Yeah.
Dirk. We'll just say
Yes,
Dirk. Like
Dirk.
just
Yes.
reading the things like and going to Stack Exchange and not even sometimes reading the answer, reading what Dirk commented about on the answers,
Yeah.
like just finding him in there. And then and this was all before large language models were a thing when we started this, but definitely in this last year, then saying, hey, I want to do this thing. Here's how I would do it in R. How would I do it in C++? Getting a template, knowing that it's wrong, and then but adapting it from there. So I'm not starting from scratch. On the
Yeah.
subject of parallelization, the only way that I was able to do it effectively is in a package development framework. So not just developing standalone C++ source files, developing a package with C++ in it, creating that package, and then exporting that to the nodes to make it work. So that when you do it that way, it's quite convenient. To try to parallelize on a single RCPP script, I never figured it out. And
Yeah.
and Dirk's comments said, don't do that. Like
Yeah, yeah, yeah.
make a package to do that. So
Yeah. Yeah, yeah, great. Thank you. Thank you, Arthur, for that question. Miles wanted to talk. So you talked a lot in this talk about like packages that you used along the way.
yeah,
And Miles has like an interesting question here about like how you do that, how you evaluate, like how do you
yeah,
decide what to use from the many, many thousands of packages that are out there and are like, did you did you lean on information or collaborators' experiences?
yeah,
Was it like trial and error a lot? Like, how did you read all the documentation and decide, that one I understand better? Like
yeah,
how,
yeah,
like,
yeah.
what in a very large project like this that involved multiple years of work, that involved multiple packages, how do you decide what tools to pick up?
Yeah, thanks for that question. And this is evolving in real time as we enter this world of large language models. So, for example, EVGAM, having a conversation, and this answers Arthur's question about what LLM I use. I use ChatGPT, and like I don't have any good reason for that. It's just that's the one I started with first. And for me, I just need to get ideas, and I'm not looking for it to. So I'm less worried about quality as long as there's like a baseline quality, and it was good enough. And so asking, hey, I want to do these things, and it gave me all these different packages, and this is something that hasn't changed over the years, going to those packages and saying, well, how many monthly downloads does it have? And so using that as a surrogate for are lots of people using this, not just because that must mean it's good, but it's easier to defend when you have to get to policy. It's easier to say everybody does this. Um, and so that was one of the reasons. How many people are downloading this package, then going into it and saying, well, how does it work? And then comparing, well, how does it compare to something I already know? So starting with, you got base, you got tidyverse, um, and then I've picked up packages SF, Terra, and you start to see examples that use other packages, and you slowly kind of build this library of things that you're like comfortable with. You go to the LLM, you go to Stack Exchange, you find a new package, you confirm that lots of people use it, and then you say, well, how does it compare? And if it's palatable, then you add it to the library and it becomes a new benchmark. Hopefully that answers the question, but it's a lot about based on popularity and previous attempts that people have made.
Yeah, yeah. Yeah, and you spoke a little bit about how you started to use LMs in this, and I know that's something that's top of mind for many people these days. Like, should I be? How should I be? What is useful? Can so when you think about you probably so you started this project before these were probably in broad use, right?
Yeah,
Like
yeah.
if, as a and then these things started becoming in more broad use. And would you? So you just said like you go to like a browser to like a ChatGPT style
Yeah.
thing to add like to use this as a tool. Is that the main modality that you used? And what would you say that modality helps you with? And when was it
Yeah.
not helpful? And then if you want to speak to like if you've tried out any other kind of modalities like completions or
Yeah.
something that's more integrated in an IDE, like tell me a little bit about it. It's kind of an interesting project to think about it because you started this project before these tools were really
Yes.
useful. And
Yeah.
like over time, what was something that you actually legitimately reached for it because it was helpful, like use
Yeah.
one of these kind of tools.
Yeah. So for me, I don't think I gave like Copilot enough of a chance. The completion style, write a comment and see what it does.
Yeah.
So I tried that and I couldn't get into flow. And so
Yeah.
I was like, I'm just gonna keep doing kind of what I know and then have the supplement with the with ChatGPT in a web browser. Um, and I mean we could wax philosophical on this with a problem project like this where the we need software so that we can reproduce what we did, but we're not necessarily putting it in production. So there's all the minutia of like, well, how are we going to handle user queries and things like that? These types of things that I think LLMs would be great for because it's pretty standard. We need to do it all the time. I'm not doing that. And so I hesitate to outsource much of it because part of it is that the code becomes an extension of thought. It's the way I'm thinking about the problem. And so I'm not even writing the code as much to solve the problem as I am to think about how I would solve the problem. So it almost becomes like a meta,
Yeah.
the code writing becomes a meta experience for me.
Yeah.
And so what would happen is I'm writing the code myself and then I get to like it, well, I need to do this really specific thing. And for me, that was a trigger. I'm not going to spend time writing something that's really specific.
Yeah.
It's well bounded, it's well posed. I can check very easily, for example, an inverse normal distribution that relies on unifrand, which is the engine for R, to be faster. Like I need it to be fast. It doesn't even have to be exactly perfect. Chat, can you give me that? It gives me it. I'm like, wow, that was fast. Okay, let's do some quick tests, QQ plots. Okay, yeah, this is working the way I expect. Let's add it to it. And so those kind of tasks are helpful. Or I'm finding I'm using it more and more for visuals. I have this map. I have this data. I want to get a map of Europe to make this plot. And that's how I found our natural Earth is
Mm.
helping it me make polygons. So when I'm in thinking mode, I don't want to use large language models. Like when I know what I want to do, I want to write it out to reinforce that. When I don't know what to do, or I only have a high level idea, I go to the large language model and just to seed ideas, but
Yeah.
not necessarily take the solutions.
Yeah, yeah, yeah. Yeah, that's very interesting. That's very interesting. Nice. Well, those are we had a little bit of a small group today, but really great questions. Thank you. Does anybody else you want to type in a question here as we wrap up? I'll give folks a moment to do that and just say the most of the questions I was wanting to ask and we kind of have addressed here, which was really great to see. And Brendan, we really appreciate you coming and sharing about your work. It was super interesting. I what I love about it compared to some of our recent talks is it's so about a specific application, and that's why we use R, right? Is like to do real problems, like to
Mhm.
do like solve real problems. And so it's really great to hear you walk through that. For folks who are here, check out the lightning talk session that we'll have in January, and if you are interested in presenting, submit a idea of a lightning talk there, well, a 5 to 7 minute talk there, and I think that's it. I think that's it. So thank you all so much for coming. Thank you, Brennan, so much for being here. I really
Yeah, my
appreciate
my
it.
pleasure. Thanks for the opportunity.
Yeah, yeah. And we'll if you want to catch this talk or send it to anybody, it'll be on our YouTube here just a little bit later when you can